The first essay question we are going to discuss is based on electricity, and the electromotive force of an electric source is defined as work done by the source on a unit charge. Using the definition of electromotive force, find the unit of EMF, and then the second question is the expression for the power delivered by an electro source in terms of EMF and EMF E and the current I through it. Fine. So let's get started. So first of all, they have given us a definition for EMF electromotive force, that is equal to work done per unit charge. That means work done divided by charge, work done per unit charge. So when you want to find the units, for work done, the unit is going to be joules. The charge, this is, they're not talking about dimensions, they're asking for unit. All right. So for charge, it will be coulomb, and finally you'll be getting joules per coulomb. Joules per coulomb. That's what they're asking. Since they're asking us to derive it, find. So this is going to be your final answer. You can also use volts for this. This is in fact volts. Potential difference also has the same definition. So this, and then second one, expression for the power delivered by an electric source. Power delivered by an electric source. For that, you can use the equation of power. You know, power is equal to work done divided by time. Usual, that is the equation. But for work done, now using this here, you can derive another equation for work done from this. What is the equation for work done? Then if you make work done the subject from the earlier case, you will be getting EMF multiplied by charge. So you can do the same substitution here. Power is equal to EMF multiplied by charge. EMF multiplied by charge divided by time. Right. Then you can say EMF E. They have given EMF is E into charge over time. I'll say charge over time. Now, instead of charge over time, you can use, we know charge over time is current. I mean, current definition for current is electric charge flowing per unit time or per second. Therefore, power finally will be equal to EI, power delivered by electric source, equal to EI. And I think we will need to use this for the latter part of the questions as well. And if they ask you to find, you have to show these steps. So we are done with part A. Now we'll move on to part B. You can see another question there, part B. What is part B all about? An electric source having EMF E and internal resistance simple R is connected to an external resistance of capital R. Obtain an expression for the energy dissipated in the circuit. Energy dissipated in the circuit in time t in terms of capital E. Right, energy dissipated in the circuit. Energy dissipated in the circuit means the total energy wasted in the circuit. So you can say energy dissipated in the circuit, that is in fact equal to, the circuit should be equal to total energy delivered by the battery. The total energy delivered by the battery will be totally dissipated in the circuit, right? So the equation now, it's going to be EI. That's what we derived earlier, but we don't know I yet. We don't know I yet. For that, what you can do is you could have gone for the circuit. No, you could have found the what do you call that? Current separately. Now think of that system here. There's a battery with internal resistance. So I'll draw the battery with the internal resistance as one system. E and simple R and capital R is here. And then there will be a current, I. And then we have to find the current. How do you find the current? It's quite straightforward. For this circuit, you can apply Kirchhoff's law, sigma E equals sigma IR. Sigma E is E. For sigma IR, you can put I capital R plus I simple R. That current I is flowing through external resistance as well as the internal resistance. Both must be taken into account. So E is equal to I within bracket simple capital R plus simple R, and finally I is equal to E divided by capital R plus simple R. And if I substitute the equation for I here, E into E over capital R plus simple R. And don't forget to multiply it by T. Now, there I think I missed this part here, small part. total energy delivered by the battery will be equal to, now energy is actually equal to power delivered, and you need to multiply that by time. All this time we did not derive the equation for energy. In fact, we derived the equation for power, EI. So they're asking for energy. So it should be power delivered into time. Power delivered is EI into time is T. So, and then what I have done, I have not changed E. I'm getting rid of current into multiplied by T. So final answer is E squared T over capital R plus simple R. Total power dissipated in the circuit means whatever the, rather energy dissipated in the circuit means whatever the energy delivered by the battery will be dissipated in the circuit. Simple as that. Right? And the answer must be found in terms of E. You can see E, simple R, capital R, and T. We have to derive the answer in that. That's what it is. Then now the next question, C part. They have given us a circuit. You can see the circuit here. They have given us a circuit, and then based on the circuit, they are asking for some questions. The figure shows an electric bulb L1 rated 12 volt, 6 watt, an electric fan F having internal resistance 8 ohm connected in series. Uh, Series is connected to a cell having internal resistance and EMF 24 volt. Now they have not given the internal resistance of the cell, so I'll take it as R naught. I could have taken it as simple R, but simple R is already given. Let's take it as R naught. Another electric bulb labeled L2, rated 20 volt 10 watt, is connected in parallel across F and L1. Right, just describing the diagram. If the electric bulb L2 glows with normal brightness, L2 glows with normal brightness means it should have the rated power around it, across it, rated power or voltage across it. Then only L2 will glow with its normal brightness. Okay, so voltage across L2, we can say it is 20 volt. When the key S1 is closed, so S1 now in the diagram you can see both S1 and S2 are open, but for this question they are saying S1 is closed. Therefore, let's close S1. S1 is closed here, right? S1 is closed. So put the switch. S1 is closed, right? Then the first question: the current through electric bulb L2, right? Now, how do you answer that? First part A1. Current through L2. Now they have mentioned that L2 glows with normal brightness. Therefore, you can go for this equation. Power is equal to VI. If it is glowing with normal brightness, it should be allowing the rated current through it. Now, they have given you the rated voltage and rated power. Using that equation, for power you can put 10 equal to, for voltage you can put 20, into current you can find. So current now, I'll mark the current. Current I will be I1. Let's say I1 is traveling. I1 is flowing. So I1 is flowing like this. Yeah, let's find I1. I1. And that is finally I1 is equal to 1 divided by 2, 0.5 amperes. 0.5 amperes. Because it glows with the normal brightness. And then the second one, internal resistance of the cell. They are asking us to find the internal resistance of the cell. Now, if the bulb is glowing at its normal brightness, you know the potential difference across the bulb must be 20 volt. We discussed about that. The potential difference across the bulb must be 20 volt. So I'll mark it here, 20 volt. Okay, 20 volt will be there. Then only it will glow with its normal brightness. Now, if I apply Kirchhoff's law for closed circuit, there's only one closed circuit, Kirchhoff's law for closed circuit. What is Kirchhoff's law for closed circuit here? It will be sigma E equals sigma IR. For sigma E, you can put 24. That is the only battery we have there. And sigma I is I1 into sigma R. Sigma R, let's take the resistance of this as R2 for the time being, R2. So the I1 into, the current is going through R0 as well as same current. I1 is going through R0 as well as R2. And if you extend it, you'll be getting 24 I1 R0 plus I1 R2. I1 R2. Now 24 equals I1 we need to find out. R0 is something we already no, I1 we know 0.5. Why is it 0.5? Because if this particular bulb is glowing at same brightness, then sorry, normal brightness, its current should be 0.5. Current through that should be 0.5. Same current should be flowing through the circuit because it's just one loop, one loop. And R0 we have to find out. Plus for this part entirely, you can use 20 volt, 20 volt, because for bulb L2, if you apply V equal IR, for bulb L2, if you apply V equals IR, what is the potential drop across the bulb? That should be 20, because it is glowing at its normal brightness, 20 equal to I1 R2. I did not find the resistance of that. So instead of I1 R2, you can directly substitute 20, because it's glowing at normal brightness. So the potential drop across that should be 20 volt. And I1 R2 is the potential drop across that according to Ohm's law. Therefore, 20 goes to the other side. 24 minus 20 is 4 equals 0.5 R naught. 4 divided by 0.5, that will be R naught. And finally, you will be getting R naught equals 8 ohms. R naught equals 8 ohms. Right, done. So that is the second part. And then moving on to the third part. The power supplied by the cell to the circuit. The power supplied by the cell to the circuit. Power supplied by the cell to the circuit. So total power delivered. You can find that total power delivered. Total power delivered. What is the total power delivered? EI. So E is 24 into current is I1. I1 is how much? 0.5. And that is 24 into half. That is 12 watt. That is the total power delivered by the cell. Okay, total power delivered by the cell. But the thing is, certain power amount of power will be wasted within the cell because of the internal resistance. Now, it is generating a power of 12 watt. The 12 watt is not given out to the now. Here, the external component connected to the battery is the bulb. Yeah, so if this is an ideal cell, ideal battery, all the power delivered by the battery should be given to this bulb, but it's not like that. It has an internal resistance, therefore it will lose a certain amount of power. It will lose a certain amount of power. So you can consider that power dissipated within the cell. Power dissipated in the cell. What is the meaning of power dissipated in the cell? That is the power wasted within the cell, and that is I1 squared R naught. That is the power dissipated due to the internal resistance. Battery will get heated up because of the internal resistance, and this is how you find it. So the power I1 that is 0.5 squared, 0.1 0.5 into R naught is 8. So that is 4 watt. 4 watt, isn't it? 4 watt. So you can say power delivered, power supplied to the circuit. Power supplied to the circuit will be how much? Will be 12 minus 4. That is going to be 8 watt. I mean, this question is not very 100% clear to me, to be honest. The power supplied by the cell to the circuit means, I'm not sure whether they are talking about the total power given by the battery or the power given to the outer circuit. So that's why finding everything, it's like just I'm finding everything to be on the safe side. This is the total power generated by the cell. Out of that 12 watt, 4 watt will be lost within itself because of its internal resistance. Remaining 8 watt will be given to the external components of the circuit. So let's write the answer this way, because it's like I'm in a bit of a gray area whether they're asking for the total power or the power given to the outer circuit. So let's write it this way. It's just a matter of few seconds, right? Right. The next question now. Find the following at the instant the key S2 is closed while S1 is kept open. S2 is closed while S1 is kept open. Right. For that, just like the previous case, S1, let's leave it open. S2, let's close it. S2, let's close it. So when you close S2, it will look, the circuit will look like this, and the current will flow through the outer part. Now let's mark the current as I2. I took earlier one as I1, so we'll take the current as I2, and that current won't flow through this part because you can see the circuit is open, in disconnected actually. So I2. The same current will flow through the fan as well as the other bulb. Internal resistance of the fan is already given R, and internal resistance of the bulb, I'll take it as R1, just like we took the internal resistance of this as R2 earlier. All right, fine. So this is how the circuit will look when S1 is open and S2 is closed. Answers: Roman 2. First part. Find the following at the instant the key S2 is closed while key S1 is open. The resistance of the electric bulb L1. They're directly asking for the resistance. Resistance of L1, it will be, how do you find the resistance? We know we can go for this equation. Power is equal to V squared over R. There's an equation for power. There are actually 3 equations for power. Power is V squared over R, also VI, also I squared R. Now, why am I using this equation? Because we have the voltage is given, the power is given. Resistance is what we are supposed to find out. Now for power, I can substitute 6 watt. For voltage, it is 12 into 12 over R2. So R2 is going to be equal to 144 divided by 6, and final answer 24 ohm. 24 ohm. That's the resistance, right? And the second one, the current through the electric fan. Now they have asked us to find the resistance of this. We know the resistance of fan, and we know the internal resistance of the battery, 8 ohm. Internal resistance of the battery. All right. So you know all the resistance. You know all the resistance. Then let's find out the current using Kirchhoff's law. Kirchhoff's law for the closed circuit. Right, Kirchhoff's law for the closed circuit. You can use sigma E equals sigma IR. Sigma E is equal to when I apply Kirchhoff's law for this closed circuit, we have already found out the internal resistance of the battery, 8 ohm. And we know the internal resistance of the fan. We know the internal resistance of the bulb, which is 24. Now we have found it. R2 is equal to 24 ohm. All right. So when you apply that, only one battery is there, that is 24 volt equal to sigma IR. I2 is the current. Within bracket, R resistance 8 plus. We'll put the resistance normally. Okay, R0 plus R plus R2. 24 equal to I2. Why do I add all the resistors like this, taking I2 as common? With the same current is going through all these resistors, series, everything is in series. So R0 we can put 8. R is also 8. For R2 we just found out 24. So 24 is equal to I2 into 40. Therefore I2 is equal to 24 divided by 40, and that should be equal to 0.6 amperes. 0.6 amperes. All right, 0.6 amperes. So this is the current. You should do this question like the previous one, because they have not mentioned that the bulb is glowing at its normal brightness. So you don't have to go for the rated values and approach this question. They have asked you to find the resistance of this. You know the resistance of the rest, then go for the Kirchhoff law. Right, now third case. Third case. So you can say total power delivered. Now they're asking for third question is total power supplied by the cell to the circuit. Cell, what is the power it's giving to the circuit? Now in the circuit you have the fan and the bulb, right? The internal resistance is inside the battery. So let's find out the same way we did earlier. Total power supplied by the cell to the circuit. It says total power generated by cell. Total power generated by cell. So that will be given by the equation EI, like we derived earlier. E is 24. This time I is 0.6. Therefore, the total power will be 14.4 watt. 14.4 watt. That will be the total power. Sorry about the connection today. It's really bad. I'm losing the connection continuously. So I'll just continue from where I left off. What I was explaining is now total power generated by cell. Generated by Total power generated by cell is EI. For E, you can put 24 into I. We found I2. We found it as 0.6. So that is going to be 14.4 watt. And power dissipated in battery, power dissipated inside battery, that means the power wastage due to the internal resistance, that can be found out as I2 squared R naught, right? So I2 squared is 0.6 into 0.6, and R naught is 8. The internal resistance of the battery is 8. We have already found it. So that is 8 into 0.36 into 8. 0.36 into 8. And the final answer is going to be 6 into 8 is 48. 8 for balance. 4 balance. 6 into 8 is 48, 8 4 balance, and 3 into 8 is 24. You add that for 28.2. This watt. This many watts. So the conclusion, answer for Roman 2, third one. So power supplied to the circuit actually. So power supplied to circuit, that is going to be equal to 14.4, the total power generated, but out of that 2.88 is wasted within the battery itself. So the remaining power will only be given to the circuit. 0 minus 8, 10 minus 8 is 2, 13 minus 8 is 5, 12 minus 2 is 10. 10.52 watt will be the net power given to the fan and the bulb when S1 is open and S2 is closed. Right. Sorry about the interruptions. I'm getting connection drops continuously. That's why it was like that. But anyways, I hope you, if you follow from the beginning, you'll be able to figure this out. Fine. Then the next part. When S2 is closed, the electric fan accelerates and reaches a steady velocity after a short time, and then L1 glows as rated. Now this part is important. L1 glows as rated. L1 glows as rated when S2 is closed. Electric fan accelerates. Okay. Right. All right. So at this stage, find the current through the electric bulb. At this stage, find the current through the electric bulb. Now we need to find the current through the electric bulb at that particular stage. For that, we can Roman 3, first part. At this stage, find the current through the electric bulb. Yeah. How do you find it? Now it's glowing at the rated current. No? Glowing at the rated current. So you can use the equation power equals VI. Power is 6. Voltage is 12. Current is I. Therefore, 6 over 12 is I, the new current, and I is equal to half, 0.5 ampere. Explain why the current present in the circuit is less than the current at the instant of closing the key S2. Now, this current is less. Earlier current was greater. Earlier current, if you can remember, it was 0.6 ampere, wasn't it? If it was 0.6 ampere, now it is 0.5 ampere. The reason for that is, people, now there's a fan. Fan has a motor, right? Fan has a motor. When a motor rotates, now this you should have learned in magnetic field. When a motor rotates, it produces a back EMF. It produces a back EMF. Now, it's like this. When you have a motor, inside a motor you have a coil which is rotating in the magnetic field, a coil rotating in the magnetic field. So a current is flowing through that and it is rotating in the magnetic field. When it rotates, when fan rotates at its steady state, now they are saying that S2 is closed. They're saying that S2 is closed. So let's close S2. And now the fan is rotating at steady state. Now inside the fan, there's a motor. So whenever you have a motor in a circuit, now fan, instead of fan, I just say motor. Always remember, whenever there's a circuit rotating, whenever there's a motor rotating at steady state, that motor will be creating a back EMF. So it will, there will be a small EMF created in the opposite direction of to the EMF existing in the circuit. So that it will be like this now, in this direction. I'll take it as back EMF, EB, back EMF. In the opposite direction, always like that. Now, for example, if you have a circuit like this, let's say you have a circuit like this, and you have put a bulb, and then some sort of a resistor, and then you have a motor like this. This is the symbol we use for a motor. Okay, right. Wait a minute, I'll draw it properly. Motor. Like this. All right, there's a motor. And now this, let's say 10 volt or something like that. This is 10 ohm and this is 20 ohm. Now this is a motor, right? Now when the motor rotates at steady state, if 10 volt is like this, motor will produce a back EMF in the opposite direction. It will produce an EMF in this direction, EB, in the opposite direction. I mean, if you think of, if you mark it as a battery, the back EMF, it will be like this time. Because a plus and plus must be connected. That means it will oppose it. Lenz law, we have learned now Lenz law. Lenz law means it will try to oppose the change occurring here. So current is trying to flow through this. Due to electromagnetic induction, the EMF is induced, and that EMF will always try to oppose it. Right? So if the battery is connected this way, EMF produced in this motor will be in the opposite direction. Okay, so overall EMF of the circuit reduces. That's why the current has reduced. Now earlier, before motor reach a steady state, you will not have that E back will be 0. Or E back will be rather, before the motor starts rotating, fan starts rotating properly, EB will be 0 or lower value. But once it's reached a steady state, it will have a back EMF which will reduce the current in the circuit. Okay, so you must have noticed in vehicles also, at the beginning, when you start the vehicle, the bulb will glow brighter, and as the vehicle starts rotating, the engine starts rotating, the bulb will become dim. At the beginning, before the engine starts rotating, the bulb will glow brighter because there is no back EMF. Once the engine starts rotating, there will be a back EMF, and the brightness of the bulb will reduce. Because without the back EMF, what will be the total EMF given to the circuit? That will be 24. Once the motor reaches a steady state, there will be a back EMF induced in that. So the total voltage of the circuit will not be 24, it will be less than 24. That's what they're asking us to find it in the next part. See, calculate the induced back EMF by the fan when it is working at a steady state. So I have written here, fan has a motor. When a motor rotates, it produces a back EMF which reduces the total net EMF of the circuit. Hence, current in the circuit will reduce. So in the circuit, if they have given you a fan or a motor, consider that as a resistor because it will have an internal resistance, and consider that as a source of back EMF. So I have marked the examples and showed you. If your battery is like this, in this the EMF will be in the opposite direction. If your battery is like this, the EMF will be in this direction. Now let's try to find that out. Third one. Now I have I'll redraw the circuit for your benefit. There will be 24 volt, and I will skip the middle part because it doesn't allow current to flow through it. And I have the fan, and then I have the other bulb, L1, isn't it? L1. Right. Okay. Now the current through the circuit is given already. Don't forget that. And R0, don't forget R0, 8 ohm. the internal resistance of the battery, and the fan has an internal resistance of 8 ohm, don't forget that, and this bulb has a resistance of no need to worry. We found the resistance, I think it was 24 ohm, right? Earlier in the previous question we found it 24 ohm, and there's a back EMF here, back EMF here. So these are the and the current we have already found. They have told that the bulb is working at its rated current, which is 0.5. Bulb is working at its rated current 0.5. So yeah, current is 0.5 ampere. Now for this circuit, you are going to apply Kirchhoff's law. Sigma E equals sigma IR. When you apply Kirchhoff's law for this circuit, what will happen? Sigma E is going to be 24 minus the back EMF, because always the back EMF will be produced in opposite direction. And in what kind of instruments will the back EMF induced? Instruments with motors. A fan has a motor, right? Equal to sigma IR. Careful, sigma IR you have to put current 0.5 into all the resistors, 8 ohm plus 8 ohm plus 24, all of them. Right, so it will be 24 minus EB, and here you will be getting 0.5 into, this is 40, isn't it? 16 plus 24, 40, 40 into half is 20. So 24 minus EB is 20, means the back EMF is how much? 4 volt. This is why suddenly the brightness, the current through the bulb reduces. Earlier the bulb will be bright, now the bulb will be glowing at its normal brightness. It's normal bright, no, normally when a bulb is glowing, no, the earlier, this is the current which will be flowing through the bulb for the normal brightness. But suddenly if it glows brighter, too bright, that means a larger current than this is going, right? So 0.6, when 0.6 ampere goes, it will be too brighter than the normal brightness. But if that current goes to a higher value, there will be a point where the bulb will break. Okay. But for a bulb to glow at a normal brightness, it's a filament bulb probably. In filament bulbs only this happens. Now normally we see filament bulbs, they will glow at a normal brightness. But when a larger current goes, when a current larger than the rated current comes, it will glow brighter. But if that current is too large, then the bulb will, the filament will burn and it will break. Okay, so the rated current is 0.5 ampere, but the current which came through the bulb earlier was 0.6 ampere. So that is okay, some a little greater than the rated current. This 0.5 ampere is the rated current. So the brightness of the bulb will be greater than the normal brightness before the fan starts working. Once the fan starts working, it will get back to its normal brightness. Okay, so it's not good to send larger current through it, because at one point when the current is too large, the filament will burn. So it's recommended to send rated current through the bulb. Right, so we have found out the induced EMF also. Earlier it was 0.6 ampere. Now, if you might have problems with why rated current is 0.5, how can 0.6 go through that? I know larger current means some current, some what do you call that? When the current which is slightly larger than this, if it flows, it's okay. But when the current gets too large, that's when the bulb is going to burn and break. Last part of this question, right? D part. A student decided to use cells each having EMF 6 volt and internal resistance 4 ohm. So when you take one of these batteries, 6 volt, 4 ohm, right? What is the minimum number of cells required for this purpose, and illustrate with the diagram how they must be connected. I think what they mean is, now we found the R0 table, that is 8 ohm, right? It was 8 ohm. We need to get a battery like this. Now the ultimate battery we need is this. It has a voltage of 24 volt with internal resistance of 8 ohm. I need to obtain a battery by connecting these cells. Okay, right. So 24 volt is important. That is our EMF, and the internal resistance is also important, 8 ohm. Now to get 24 volt, how many such these batteries will I need? I will need 4 of those, right? I can put 4 of those, right? I can put 4 of those to get that 24 volt. That is 6 volt here, 6 volt here. Right. 6 volt here, 6 volt here, right? So 6 plus 6, when they put the batteries in series, their EMFs can be added, no? Right? But there's a problem. The problem is this. Now look at the internal resistance here: 4 ohm, 4 ohm, 4 ohm, and 4 ohm. Right? Now this system is equivalent to a battery of 24 volt EMF and 16 ohm resistance. 24 volt EMF and 16 ohm resistance. But what we need is this. We need a battery with 24 volt EMF and 8 ohm internal resistance. So if you put a system like this, it's incorrect. Why? Why was I tempted to draw a diagram like this? Because using these batteries, these kind of batteries, I need to produce 24 volts. The only way to produce 24 volt is putting 4 in series. But when you put 4 in series, resistance becomes double the value we expect. The value we want is 8, but the resistance is double. So what's the only solution we have? You can put such another system like this in parallel. Now what level? Tell me. 6, 6, 6, and 6 here, and then you put it parallel again, the same similar. Now what happens when you put system parallel that like this? Right, this is one system. Huh? Every battery has a voltage of 6 volt. Quickly draw, write it: 6 volt, 6 volt, 6 volt, and 6 volt. The reason is, okay, the internal resistance of each battery is 4 ohm rather. 4 ohm. I'm talking about these batteries, 4 ohm. Right? Why did I put two such systems in series? Because parallel, because I want the resistance to be 8 ohm ultimately. But if I put just one line, one row, I have 16. So I need to halve the resistance. The only way to halve the resistance is put another equal resistance in parallel. Now, when you put them in parallel, now you can convert this system to this. All these together, you will be getting 24 volt, and here 24 volt. Okay, all these together, and here you will be getting 16 ohm and 16 ohm. 16 ohm and 16 ohm. And then when you want to, when you simplify it further, 24 volt and 24 volt equal voltage parallel. Equal voltage parallel means EMF, it will be still the same. That's how batteries work. When you put two batteries of E and E like this, the resultant EMF is also E. It's not E by 2. You have to understand that. It's a voltage source. So the same voltage will prevail, right? But 16 and 16, they are resistors. When you put resistors in parallel, the resultant resistance will be half of 16 and 16, 8. So this is what I was supposed to get, because that is the electric supply source we have here, right? So that you can get it if you use a setup. This is the answer for this question. If you ask me, this is the answer for this question. This is going to be the answer for this question. But I just wanted to explain you how that answer was obtained. If I had just drawn like this, you would have confused, you have got confused people. So I wanted to show you step by step. Right. So this is the final answer.